So, welcome to this lecture on the characteristic properties of a transistor region. So, basically, when we are talking about the transistor, we have already seen that a transistor has got three regions which are known as the emitter, base, and collector. So, I'm writing for you that we have got three regions which are known as the emitter, base, and collector. So I'm writing it in a short form. So now we will be talking the characteristic properties of transistor region. And first we are talking with respect to the width of each region. So when we are talking about the emitter, base, and collector, so let me draw it for you. So we are saying that we have got a emitter, then we have got a base, and then we have got a collector. So basically when we are talking about the base, we say that this base is very thin. Okay, so I'm saying that this base is very thin. Okay, so let me highlight it with this base is very thin. So I can write that the width of B is minimum. And for the sake of nomenclature, I can use it as a WB. Then what we say is that the E is medium. The width of E is medium. So I'm saying that this E is large than the base. The width of a meter is large than the base, but less than the collector. So I'm writing here that the width of the E is medium. Okay, so I'm writing it with respect to the W E. And finally, what we are saying is that the width of the collector is maximum. So this collector which we are drawing here is maximum. So we can write the width of this C collector is maximum. Okay, so we can write it as a WC. Okay, so we can say that WC is greater than WE and WE is greater than WB. Okay, but how much greater? We are not talking about this, right? So this is the relation that the WC is maximum, WE is medium, and WB is minimum. Okay, so we have got a reason that why we are talking about this base to be a minimum. So when we are talking about this base to be a minimum, we say that we want to keep this B as minimum because this is to this is to minimize the recombinations. That means whether the holes or the electrons are traveling from the emitter to the base region, so there will be less recombination of this electron hole pair. Therefore, we want to keep this as a minimized. Okay. And when we are talking about this WC, we are saying that we want to keep this WC to be the maximum. Okay, because this is being used to minimize the power dissipation. Okay, so this is to minimize the power dissipation. And the power dissipation we are calculating with respect to the per unit surface area. So I'm writing this is to minimize the power dissipation per unit surface area. Therefore, we are making this collector C to be a wider. So whenever you will going to see whether we are talking about the NPN transistor or the PNP transistor, this is the actual thing which we are doing. But when we are drawing it conventionally, we are not showing this emitter and collector of unequal length. We are showing it for the it as a equal length, but they are not of the equal length. So when we are talking about this collector, that we are making this a collector a wider, why we are doing it is because when we are going for the transistor operation. So what will going to happen is that the current will going to flow as this collector is collecting all the charges. Okay, and when this collector is collecting all the charges, okay, the heat will going to be produced at the collector junction, and therefore to minimize this heating effect, okay, the collector is made larger to dissipate this heat which is being produced by the charges. Now coming to the second property. Okay, so the second property which we are talking is with respect to the doping. Okay, so when we are talking about the doping of each region. When we are talking about the doping of a NPN transistor or PNP transistor, so I'm drawing here a transistor. Okay, so now instead of writing the NPN or PNP transistor, what we have seen that we will going to have a emitter, base and collector. So I will be writing here emitter, base and collector. So when we are talking with respect to the doping, we have seen that when we are talking with respect to the emitter, so emitter is being heavily doped. So I'm writing it here. This emitter is being heavily doped. Why we are heavily doping this? So that it can inject large number of charge carrier to the bases. Okay. So I'm writing so that it can inject a large number of charge carrier, okay, into the base. Now, the charge carrier can be your electron or the hole, depending upon that whether you are using the NPN transistor or you are using a PNP transistor. Then we have got a base. So we can say that base is lightly doped. So I'm writing here that base is lightly doped. And lightly doped means we are talking about that it will be having less impurities in it, and we have already seen that this base region is very thin. So the purpose is that it will going to pass most of the emitted injected charge carrier. So whatever the charge carrier these are coming from the emitter, it will going to pass it to the collector. Okay, so there will be very less recombination of the electron hole pairs will going to occur. Okay, so what we can write here is that it is being lightly doped so that it passes most of the emitter injected charge carriers to the collector. And finally, we have got a collector. Okay, so we have got a collector, and we say that this collector is moderately doped, or we can say it has got a medium level of a doping. So we will going to write it here moderately doped. Okay, and when we are talking with respect to the moderately doped, is means that it is less dope compared to ammeter. So this is the doping of each region. So I'm writing this ammeter is maximally doped, and when we are talking about the base, we will going to say that base is lightly doped, and when we are talking about the collector, we say that collector is mediumly doped. So this is the doping of each region.